And we are recording. Nice. So, tell me, please, some basic terminology. What gas is, why we use gas and not near, what does it mean to charge gas, what does it mean to burn gas, in that area. Yes.
Okay, yes. So gas is currency you could think of that we use to pay for execution on near blockchain. And the workflow is a user submits a transaction on chain. We compute what it costs to execute this transaction, and we calculate this in number of gas units. And then there's a dynamic gas price that makes a conversion from near tokens to gas units. And that dynamic price is taken and to convert how many near tokens that will cost. And then from the user, we subtract the near tokens that was required to execute the transaction they want. On a very fundamental level, we need this as a way to protect ourselves. So if everything is free, then denial of service attack would be super easy. Anyone can just spam transactions. So we want some way of assuming, making sure there's a fair sharing. Someone wants something to be executed, so they should pay for something. In other blockchains, often gas is directly given to the validators. We don't do this. So other blockchains might explain they need gas because validators need an incentive to execute it. That's not how our incentive model works. Validators get like a fixed amount of rewards, even if there is very little traffic. So their reward doesn't depend on traffic directly. We actually just burn the gas, and that means you purchase gas with near tokens, and those near tokens are just burned. They're removed from the total. And that indirectly incentivizes validators maybe, because the total shrinks, so their part of it becomes more valuable. But that's like a tiny, tiny effect. I wouldn't say this is actually the incentive. It's mostly about making sure it costs something when you want to execute something, so that the incentives for, like denial of service attacks are not really possible, or at least it should cost something. And I think that's like the basic economics and idea of how we use gas.
Okay. So we can now jump straight into the juicy part, the code of it. What I assume the hardest part is how we calculate the gas charge, but there's the parts around it in runtime that may be useful. I don't know. Can you throw something around this? I don't know how to formulate it better.
Maybe before we jump into code, a couple of implementation difficulties that I can explain without code. So one thing is we don't know ahead of time how much gas it will cost in all cases.
Yes.
So if we create a new account, that's something we can pretty much know what it will cost because it's always a fixed amount of work. But when we execute a smart contract, that is a Turing complete program. We literally cannot compute ahead of time how long it will take to execute. We have an upper limit because we just stop the program after a certain amount of gas, which technically makes it not Turing complete, but really into technicalities at this point. Main point is like we don't know how many iterations of a loop are going to happen inside this execution before we actually execute it. So if you want to protect ourselves from executing too much, we have to make some estimates before we start executing. And our solution is basically we assume the worst case. So we just when we start executing, we assume, well, okay, it's going to use all the gas it has. And we only under this assumption, we're actually going to execute it. And even that doesn't quite work always. So we have an interesting way of filling up our chunks. But roughly what we're trying to achieve is within one chunk, we should only have 1 second of compute workload. And we try to match gas units with time it takes to execute something.
Yeah.
So that's like an additional step of what gas is. It's not just money, it's also time, compute time.
Oh, do you know some back of the napkin estimations for gas to seconds of estimation of computing?
Yep. So 1 petagas is 1 second.
Mhm.
Or most often we kind of use teragas for 1
Mhm.
millisecond. 1 millisecond is 1 teragas. So
Okay.
yeah.
Yeah.
At the end of the day, you can use anything you want, but teragas seems to be most useful. Often you think in milliseconds. And 1,000 teragas equals 1 petagas. That's what we put in a chunk. Now, the filling is a bit interesting here because when we start executing a receipt, we don't know how much it will take. So we don't have a hard limit on 1,000. What we do is, as long as we're below 1,000 teragas, we will always add a new receipt. And once we start working on it, we will always finish the receipt. Which means in the worst case, we are at 999 and we add another one that takes 300. So we can actually go with gas up to 1,300 teragas. But that is then a strict limit. It can never go above that.
Oh. Okay.
Yeah. Maybe now we can go into code.
Yeah.
Look at some places. Present screen. Let me see. Do you think that's large enough for the recording?
I mean, if you can make it bigger, if it will not hurt.
I can always make it bigger. It's just we see less and less at the time.
Okay.
Okay, let's try this way. So first of all, we are here in the runtime source lib.rs file.
Mhm.
This is basically where our transaction runtime lives and like where we execute transactions and receive. This apply function applies a list of incoming receipts to the current state, and there's also a list of transactions. We're not necessarily going to execute all of them, we just execute as many as fit. And then everyone deterministically has the same list that belongs into it, because the gas calculation is, it doesn't depend on any like local time measurements. It's always, we do a bunch of work and then we count that piece of work in number of gas units. So everyone will have the exact same counter, and maybe from 100 receipts, everyone will execute the exact same 32, and the remainder will be postponed to the next. It's delayed, I should say delayed. We have a concept of postponed and delayed receipts. These are the delayed receipts.
What is the difference?
Delayed receipts are those that don't have enough gas, like that didn't fit the chunk. Postponed receipts are those that are waiting for a data dependency.
Okay.
So you have like a promise chain, then you have to wait for the result before you can execute it. Those, I think those are postponed, but maybe I'm confusing names here as well. Okay, so for gas, here we are in this apply function, and the first interesting step in here, I think, is process transaction here. So it's a loop through the transactions, and we process them one by one. Each time we apply it, we will receive we will burn some amount of gas. So let's treat this as black box for now. We process a transaction. Something happens with the transaction. That doesn't mean we execute all the actions inside. We actually only accept the transaction and convert it to a receipt. So I sign a transaction that I want to execute the function call on contract B. First, it will go on my shard, verify the signature. That's what we do in process transaction. And then it will produce a receipt, and that will be sent to contract B's shard, and that will execute there. So that's step one. And here, after processing it, we have a number of gas. Here in the outcome, we have a number of gas burned. And we use save arithmetic to add this here, so we don't have any overflows. And then we increase the total gas burn counter. And somewhere below here, we should be checking that this is not over the limit. Total gas burned. Save that gas. It's hard to read.
You can decrease the font if you want.
Let's see. So here we have total gas burned. Oh, well, okay. We've recently changed it to total compute usage. That makes sense. And we are now checking on compute usage. I think for the purpose of this conversation, we should just assume compute usage equals gas and not worry about the difference. But then you have a limit, and here we're executing receipts until compute limit is reached. Up here, we are still processing transactions. But the tricky bit here is, I think like at some point, there's also a check for when we're above 500 teragas, so half of the full space we can use for transactions. And if it's above that, we will stop with the transactions. But I think this check is actually done outside. So what we receive here, this list is already truncated to only 500 teragas for the transactions. For the receipts, we don't have the luxury. We can't truncate. Like a block producer, or I should say a chunk producer, can decide which transactions get in, and they will only add as many as 500 teragas can fit. For receipts, you just have to execute what's there. So these can be incoming from all other shards, and you just have to accept them. And you can execute as many as until the limit is reached, which is 1,000 teragas. And everything beyond that, you have to delay it, put it in a queue. And you can easily see that there's a bit of a problem here. If we constantly have more receipts incoming and we can execute, then the queue just kind of grows to infinity. That's roughly the congestion problem we're trying to solve at the moment. So that's related, but not the topic today. It's like process transaction is here. After having processed them, we have processed receipt. And again, we add gas burned. And at some point, we reach the limit. And we stop. Like here, okay. Yeah, in this loop, this is a closure we put here somewhere on the stack to do all of this code here. It's a bit hard to read. Don't worry about the details. The important part is here we loop process receipt until we are above the limit, and then we delay all the remaining receipts. And delaying can be a bit costly because you have to write them to disk and whatnot. But yeah, all of this is kind of accounted for. Now, how do we figure out these gas numbers. From this view, all we see is in the outcome, we have some compute usage or gas usage, whichever we are more interested in, of like a gas burned value. And let me actually jump in here. We have a gas burned counter on this execution outcome. And we also have a tokens burned value. And we need both of them because depending on the gas price, the ratio between the two will be different. So yeah, we always keep both of them. Tokens burned will be removed from the yeah, let's actually talk about that. When are we removing tokens where? When we process the receipt, in that stage, we remove all the tokens from the user that signed the transaction. And we prepay a lot of gas, like all the necessary gas that the transactions and all the following receipts will consume. And we have to do it there because when we're on the next chart, then we can, like we're on the wrong chart to subtract tokens from the original user. If we had the model where the contract pays for gas, then we could do it in every single step. But because we want the user to pay for it, you have to do it ahead of time. And to make that possible, there is a bunch of complications now. So first of all, you have to look at the list of actions you're going to execute and figure out how much gas each of them will cost. And for function calls, that's difficult. And that's why if we look at actions.rs and then we look at function call action here, well, let's go to the definition. This action, you have to define an amount of gas you're willing to spend. For the other actions, you don't need to specify it. It's a fixed amount, but here you have to specify it. And then we purchase that amount of gas on top of the base cost. And then all the following receipts just draw from this pool. And as soon as this pool reaches 0, the receipt will be failing. And it will fail deterministically on all nodes at the same time with the same error. Even within WASM, it will fail in the exact same operation. So it will have like, maybe it was able to make 10 loop iterations and then it stopped. It doesn't really matter that we are that accurate. The important part is that everyone agrees that the receipt failed, and when it fails, there is no state change to the account state. We still burn the gas and like actually make them pay for it. So that state does change, but the account didn't make any changes to its own state. Okay, so here is one more complication. When we pay for this gas, we don't know the gas price yet. So the price is the ratio between token and gas, and that could change in the future. And for that reason, we have a pessimistic gas price calculation that will extrapolate into the future. Like, okay, it could be that we're executing the received 10 blocks in the future, and in every block, we could have an increase of, I think, 1%. And then it basically calculates what's the worst case, what's the highest price that it could be. And based on that potentially highest price, we have to purchase the gas. So if we go back to here, and let me just search for process transaction here. Yes. This function, let's verify and charge transaction. And then that's a match. So always a bit confusing to read. So we have this large call. Then we have a match, and the result gets in here. Let's actually go inside first. So we have validate transaction. This returns a transaction cost, and the cost is a number of gas burned, gas remaining, and received gas price. And that's what I was looking for. So the pessimistic gas price used while we purchased the initial receipt gets written in here. So let's say the normal price is 1, and then it decides, okay, but pessimistically it's 1.5. We write it in this transaction cost result, and this is now inherited by all the following receipts. So each receipt will know it has purchased the gas at this price. And then in every step, when we burn gas at the current price, and the current price is lower than this pessimistic price, we calculate the difference and refund the difference. And at the very end, whatever gas is left, we also refund it and calculate it back to tokens using this price that was originally put in here.
And it's a bunch of different refunds, right?
Yes. So it's an every, if you have a function call chain of like 5 calls, then you will have 5 refunds. You can merge, like in the last receipt, you will have a refund for the difference between gas prices, like the actual price and pessimistic price, and you will have some leftover. So this is merged to one single receipt. So, but in all the other steps, it's like these happen at different times, and so we actually have to produce different receipts. So it's a bit inefficient here. We're also there. These refund receipts are also completely free. We don't charge extra gas for it. We still take it into consideration when we fill our chunks, so that they're not. It doesn't take too much time. But economically, it's free. Yes. So in the last minute, what I want to show is maybe we've already been here in like verify and charge transaction. And then in here, we've seen validate transaction will return this cost. So how is it computed? And I'm just going to show one example, and then you can kind of think about how the rest will be done. So we have a bunch of verify stuff, and then in the end we have transaction cost. This function is where the cost is, where transaction is computed. You have a similar one for receipt cost. And the transaction cost has a base cost here, which starts here, and that's the example I want to show. We look up in the config. So there's a runtime fees config, a parameter passed in, and that can be different for each protocol version. So we can change the fees for protocol version. So here we assume we get the right config for the right protocol version. And then we look up what is the fee for a new action receipt. Without any actions inside, just an empty new receipt, what's the cost? Then we read the send fee. We always have 2 parts, the send and the execution part. Now we are on the sending side. So we only look at the send cost. And then we have to say whether the sender is the receiver. Because if both sender and receiver are the same account ID, then it's a local receipt. And at least in theory, these could be cheaper. In practice, we have the same cost in virtually all the places. So like for all purposes that it matters, it's the same cost. But we have the option to make it cheaper if it's a local receipt. And that just returns a gas value. And that is one specific parameter that we're charging. Below here, you can see at some point we have to go through each of the actions inside the transaction and charge for each of those. And here we have like another helper function, total send fees. and a bunch of other stuff that I don't have time to go into. But total send fees in here, you will see a loop, as you might expect, over all actions. And then for each action, we look up the fee in a very similar way. Like we take this config fee, and we have this parameter here and the send fee. Just add all of these up and return the result.
Oh.
So
Much less scary than I expected.
less scary, or
Less scary, yes.
okay, yeah, I'm happy.
Yeah.
It shouldn't be that scary, but yeah, the devil is in the detail when you actually have to change something.
Yeah. Well, that was amazing. Thank you. Thank you very much.
Okay, cool. I hope it helps.
Yeah, I hope it helps somebody else besides me. It definitely helped me. Thank you.
Cool.